So when we take a look at the Earth, we can see that it's mostly composed of four main elements, two that definitely dominate everything. We see that most of the Earth's crust is dominated by the presence of oxygen and silica. When we see minerals that have silica and oxygen in them, we call those silicates. We can also see that there's two other main elements here, iron and magnesium. When we see the elements, or when we see minerals have iron and magnesium in them, we call those mafic. These are the two dominant groups that we see, with silicates obviously being the most common rock-forming minerals. So let's take a look at these two major groups. If we look at silicates, like I said, silicates definitely dominate the landscape as far as mineral types we're going to find. The second most abundant mineral that we can see is quartz. And if you take a look, quartz is composed of nothing but silica and oxygen. It has a pretty good hardness. Its hardness is about a 6. However, you can see that the color varies, right, wildly, due to the impurities. So again, that's why we can't use color as a defining characteristic. We're going to see that quartz is going to play a very important role when we start talking about environmental types, because this is going to be the main component of beach sand. If we take a look at other silicates, one of the most common silicate that we find is feldspar. It is 60% of the Earth's crust, so it is definitely the most dominant. It comes in two main categories. We have orthoclase feldspar and plagioclase feldspar. The main difference is one contains potassium and the other one contains calcium and sodium. If those of you that took physical geology, you may remember how that plays into it on Bowen's reaction series. Those of you that have no idea what I just said, totally okay. If we look at some other silicate groups, our micas are definitely the next common. Micas are pretty interesting because, as you can see in the picture here, they have one direction of cleavage. So they split apart, right, in those nice flat planes. Two very common silicates that we're going to see are muscovite and biotite. Muscovite is the one in the picture. It's clear or kind of silvery colored. Biotite is very dark. It's black or dark brown. And the reason why we have these two different groups is muscovite is a silicate, right? It has more silica and oxygen. Biotite has more iron and magnesium, giving it that darker color. Our next two common groups are amphiboles and pyroxenes, which you can see, they both look pretty similar here. They're both very dark in color, telling us that they have a little bit more iron and magnesium in them than just, say, quartz, for example. The way that we can tell these two apart is by looking at their cleavage angles. Amphiboles have cleavage that doesn't sit at 90 degrees, and pyroxenes have it that do. That's really the only way to tell these two groups apart from each other. And our last two silicates are olivines and clay. Olivine is August's birthstone, right, my birthstone. It's green in color because it has a lot of magnesium in there. This is a mineral that actually forms way down deep inside of the Earth, and it's brought up by igneous processes. And it's very unstable at the surface's low pressure, so that's why it kind of breaks apart. If you look at it, it kind of looks like it's broken apart into these little tiny crystals. And then clay minerals. Okay, clay in general tends to be silicates, and that is definitely very common, especially if you've ever driven across Mississippi. Now let's take a look at some of our very common non-silicates. The most important group that we're going to talk about of the non-silicates, because there are a bunch, is the carbonates. We're going to talk about the carbonates a lot, especially in Chapter 5. We'll talk about that throughout the rest of the week. But three main minerals that we're going to find in our carbonates is calcite, which is this guy right here. Calcite is easily identifiable because you see it forms a cube, but the angles aren't at 90 degrees, so it's kind of a drunken square. But it's really easy to tell if you've got any carbonate because all you have to do is put hydrochloric acid on it and it starts to fizz. But notice our carbonates all have this CO3 ending to them. Calcite has calcium, it's a calcium carbonate. Aragonite, interestingly enough, is also a calcium carbonate. You see it has the same chemical formula. What makes this different is aragonite is what we tend to see in living organisms. So we tend to find this in the shells of mollusks or in corals. Now what happens is after, say, a clam or a snail dies, the chemical, the way that these chemicals are combined together, their bonding structure isn't stable anymore. So once the animal dies, it actually reverts to calcite. So aragonite is what we see in living organisms, and it turns into calcite after the organism dies. And then the third most common non-silicate mineral is dolomite, which you can see what makes it different is it has magnesium in there. And then our last more common non-silicates are our evaporite minerals, which I would hope you can tell how they form given their name. They form through evaporative measures. So when a lake bed dries up, it's going to leave behind minerals, just like we talked about in the last chapter with the formation of the oceans and how they got salty. So two very common minerals that form from the evaporation of water are salt, right? That is by far the most common on our planet. Salt, like I said, is dissolved in all water, whether it's fresh or seawater. And gypsum. Gypsum, like I said, is the main constituent that you see in your drywall or your sheetrock at home. But it also forms the same way as water dries up.